Hello and welcome to Physical Chemistry. Unfortunately, I'm not going to be able to be with you in class today, so I'm going to record the lecture so that you can have the notes. So the last time we met, we were talking about Chapter 18, the partition function and ideal gases. And so in our discussion, we had talked about how the partition function for the monatomic ideal gas has a couple of different components. We talked about how it has the translational and the electronic component. That gives it two different terms in the energies, one for each of those, and then it also has the corresponding two components in the partition function, which I've written up here. And we also talked about how the partition function is going to be a function of both volume and temperature. Now the translation has volume and temperature dependence, whereas the electronic only has temperature dependence because the electrons are, bound to the nucleus, and so the volume element really shouldn't be that important for where the electrons go. Then we had been working on developing what exactly the equation for the translational form is going to be, and we had talked about how we can derive this from the particle in a box model. And from quantum mechanics, we have an expression for the energy, which we have been attempting to solve. Now the problem is that this is yielded a sum of many terms. And the problem is that this sum is not convergent, and so we can't solve it. So in order to deal with that, we are going to fit this with an equation, and then if we integrated the equation, then we would be able to get an answer. So this is the approach we are going to take in order to solve for the energy. This represents the form that we had gotten from our sums, right? So it's like Riemann sums from calculus. And so here is our functional form, which is going to fit onto those. So then what we can do is we fit this function on here, and we get this functional form right here. So it's going to be an exponential equation, basically to represent a decay. Some other things to notice about this equation right here. So we have e to the negative beta h squared n squared over 8ma squared dn. What we notice is that this is raised to the third power. So why is it raised to the third power? This is because we're talking about translations, and so translations have equal components in the x, y, and z axis. Having components in those different axes and having the axes be equivalent to each other, we therefore have a three-dimensional problem, and so this 3 right here is there because basically we have one of these for each dimension multiplied together, which it just makes them cubed. So therefore we have this, this equation here that will give us the area under the curve for one dimension, and then we cube it in order for it to apply for all the dimensions. So when we perform the integration, which I'm not going to take you through in every single step, we can basically just use tables to solve this integration. When we solve that, we get the Q trans of V and T is going to be equal to 2 pi m kBT over h squared, and this will be raised to the 3/2 power, and this is multiplied by V. This will be equation 18.6. If you want to follow along in the text. Alright, so this is our solution to the problem. So then once we have obtained what a partition function is, then we can write some useful expressions using the partition function. So we've kind of already started to see this trend being followed along, and so from our previous discussions you might imagine that one of the things we would want to write is going to be the average energy. This will of course be the average energy pertaining to the translation. So let's write our expression for the translation. All right. So now that we have our Q, we can write the average energy of translation is going to be equal to kBT squared, times d ln Q trans over dt with constant volume. So this little v down here is reminding us that the volume is going to be held constant. Alright, and so then what we would do is when we have a particular q for our partition function, we would substitute that q into this equation right here, and then we would perform the derivative with respect to t. That is, we make t be the variable, and then we solve the equation. Okay, and so then if we actually plug in the terms that we have just solved for, and we apply this derivative, the result would give us that this is going to be the familiar 3/2 kBt, which we have seen from general chemistry, and so this is where that energy is coming from. It's coming from the translational component of the partition function. Alright, so that handles one of the two terms that we were talking about, but we also have the electronic partition function, and so we haven't yet discussed where that comes from. So let us consider next where the electronic one comes from. So just to remind ourselves what we're talking about here, let us draw the Bohr model of the atom. So here's the nucleus, and we're going to draw the shells, right? So you remember how we put the electrons into the shells? Done this probably in general chemistry and so forth. So we got 1, 2, 3, 4. So we need one more. Alright, there's our Bohr model right there, and so we'll have n equals 1, 2, 3, 4, and 5, and of course there are an infinite number of shells, and that will just help us to remember what we're talking about. And then we would also like to draw the energy diagram, so I'm going to put a diagram right here. Alright, and so for our first states, these are going to be the energy levels. And though on this axis I'm going to have the energy, which corresponds to it. When we have our first energy level, that's going to correspond to an energy of 0. And as we move up, we're going to have the energy levels be increasingly closer together. So we've got 2, 3, 4, and 5. So as I've drawn them here, the energy levels 1, 2, 3, 4, 5. As we move further out from the nucleus, what we're saying is that the energy is getting closer and closer together. And so that is our basic model, and so we should have this model in our heads as we're thinking about the electronic partition function. So now what we're going to do is now we're going to actually write what the electronic partition function is going to be. So Q electronic is a function of T, because it's a function of temperature, is going to equal the sum of ch18 e to the negative beta e to the ei. This is equation 18.8 if you want to follow along. Okay, so let's actually just define what our variables are. So I is going to be the electronic levels. So the i's are representing these levels right here. G is for degeneracy. So we've actually seen the degeneracy in the bead models already. So this means that if you have two energies which are going to be the same value. So when we think about electrons, we should think about, for example, the X, Y, and Z and the P subshells. So when you draw the lobes in Gen Chem with the PX, PY, and PZ, we have 3 different orbitals and they all have the same energy, they just differ in their orientation. So we're going to have a degeneracy term so that we could take into account energy levels which are the same value. So the degeneracy number would basically just tell how many how many orbitals have the same energy. And so this epsilon this is going to be the energy at the ith electronic level. Right, so as we said, the energies are going to be different for each of the levels, and as we go out, they'll be increasing, but the rate at which they increase decreases. And so E is the energy level. All right. So then if we want to actually write out our sum, then we would need to just write out the energy for each of the terms. And hopefully this will help you to actually see how this equation really works. Q elect of T is equal to, and then so we actually write the sum. So the degeneracy of the E1, e to the negative beta. So this is then the energy of E1, right? So now we're going to have the beta times, so this is, remember that beta stands for 1 over kBT, so that's the Boltzmann factor, and which is kB, and T will be the temperature. So this is taking into account the temperature and the Boltzmann factor. And the Boltzmann factor, again, mainly is dealing with the ideal gas, right? Because remember that it has to do with R over Avogadro's number, really. So that's all what's inside of the beta. So we have the energy levels. So we're saying the energy at this position here, which is going to correspond to energy of this over here. And so we have negative beta e to the E1, and then we're going to continue our sum. So we're going to have G to the E2, e to the negative beta, e to the E2 plus, and so forth. So we'll have an infinite sum of all the terms, and we would sum out to the number of levels that we are going to discuss. Okay, so we note that it's a function of t. Again, we have mentioned that. The t is actually inside the beta, right? And so it's not a function of volume, and the reason for that is because the volume really shouldn't be the main place, the main factor where the electrons go. So it's true that the electrons actually are not necessarily bound to their center, because we know from quantum mechanics that the probability for the electron needs to be taken from the integration over all space. However, most of the time it should be bound to its nucleus, so we would say that effectively the volume really shouldn't matter, especially in the way that the volume for translation matters. Right? So when you have a particle translating in XYZ space, it could be in any of the 3 dimensions. And so this is why we don't have the volume element in this equation here. Okay, so also typically we usually only need the first 2 terms, so I've actually only drawn out the first 2 terms explicitly here. And the reason why is because for temperatures less than 1,000 Kelvin, these typically are going to be the majority of the answer is going to be contained within the first 2 terms. So we usually don't try to calculate it out to more terms. And so 1,000 kelvins is pretty hot, and so if you're going to be studying a biological system, or most of the systems that chemists would be studying, unless you're studying, like, I don't know, chemistry on stars or something like that, being below 1,000 Kelvin, it should be quite fine, and so using 2 terms will be great. So now we have figured out how to do the Q translational and the Q electronic. So those are the partition function components for the monatomic gas, and so then that is all of the terms that we need in order to have the complete partition function for the monatomic gas. And so then, knowing this information, there are related useful properties. So we might actually want to look at some of those. So not surprisingly, we have some functions that are related to the ones that we've already talked about. So for the monatomic gas, all right, so what do we have? So, related useful properties. For the monatomic gas. All right, so what are the related useful properties? How about the average energy? All right, so we're going to have U is going to be equal to kBT squared times, and now this is going to prescribe a derivative, dlnq over dt with the n and v constant. All right, so why did we switch to big Q? Well, big Q is when you have all of the components for the entire system. So therefore, since the system only has the two components, which we have now learned how to solve for, we now have the grand total, right? So we have the total for each partition function, which is the Q translational and the Q electronic for this system. But the total partition function then for the monatomic gas, which is the sum of those two, is the grand total for the system. And so the grand total is big Q, and that's why we've switched to using big Q up here. So this says you would need to take the ln of the both components of our partition function, and then we would take the derivative of the log with respect to temperature. Now we're going to have this be a constant n and constant v. So what's big N? Well, big N is the number of particles in the system. So why would we hold n constant? Well, it probably wouldn't be a very smart idea to change up the number of particles in your system in the middle of doing the experiment. So that would mean, like, as you're doing your experiment on some volume of gas, you pump more gas into the system. That's probably not what you should be doing. So that's why n is constant, and we're also doing this under the conditions of constant volume. We also have our kVT squared factor out in front here, so that we have our temperature and Boltzmann constant taken into account. So that's how we get the average energy. This is actually equivalent to n kVT squared, and this has the derivative dlnq. So here we're going to have for the individual parts. So if you want to break it out into the individual parts, you can get the energy for each part, and then what we would do is we would multiply by the n over here instead of having the n be held constant, and so then you can get out the parts. And so then if we would like to actually write what those parts are, we can actually do that now because we had solved for each of the Q's. So that then would be equal to 3/2 n kBT plus, so this is going to be our average kinetic energy, and plus our electronic contribution. So we could write NGE2 epsilon E2 e to the negative beta E2 plus, and so then we would have our next term, so that was going to be n, we're going to run out of space here, GE3 e to the power of e to the negative wait, so this is going to be epsilon, so it's going to be epsilon E3 e to the negative beta E3, right? So this will be, this goes in here, right? So we're going to then just have the sum of the terms and so forth, right? And so this is the average electronic energy. Okay, so then what happened to the first term, right? You see it starts with GE2, e to the E2, blah, blah, blah. How come we don't have the E1 term? Well, that's because the first term for GE1 does not appear in the average because we took the derivative, and when we take the derivative, that term drops out. So you see this one up here has got the derivative in it, and we've taken the derivative over here. We've also noticed the t squared has dropped down, right, and so forth. So when we take the derivative, the first term drops out, and that's why we began with the second term. All right. So then that concludes our discussion on the monatomic gas. So basically what we've done is we have been able to solve using two parts to the partition function, because that's all you have with the monatomic gas, and we have been able to solve each of those parts exactly. and then we were able to take a look at some of the useful equations that result once we know what the partition function is. And among those important things would be the average energy, which has given us the familiar result from general chemistry. And we can also, as we've done here, write out the actual total energy. So the next thing we're going to discuss then is the diatomic gas. So, in order to discuss the diatomic ideal gas, let us call to mind what our model is going to be. Alright, so the diatomic ideal gas looks like this. Okay, and these are going to have two masses, so we have M1 and M2. The masses are not necessarily having the same value, that's why they're labeled separately. And they're actually going to be connected by a spring, so I'm going to put a little spring there. And so then our E total is going to be given by the E translational. Oh, we're going to write these actually as epsilons. E translational plus E rotational plus E vibrational plus E electronic. Okay, so what we notice here is now we have four terms. And so why did we have these new terms be added? Well, let's take a look at what we've got here. So the translational one right here, this is a familiar one which you've already seen before, so that's going to be about the molecule translating in space, and so that's fine. And we've also seen the electronic one before, so this one should be kind of similar to that, right? And the new terms are the rotational and the vibrational. So you don't really have a rotational term when you have just a point, right? Because it's pretty much infinitely symmetric. And so now that we don't have a point anymore, now that we have this diatom over here, then we're going to need to have a rotational term in there. Also, when you have just a single point, you can't really have too much going on for vibrations. And so now we've introduced this spring in here, and so this is going to talk about the vibrational motions of the masses with respect to each other, so to describe our diatomic molecule. So then, our task looking at this is going to be to modify the translational and the electronic to have the differences that this new model is going to bring from the monatomic model. And then we're going to need to figure out what these terms are going to be over here. So these are the new ones. Alright, and so then we begin our discussion using the results from the rigid rotator harmonic oscillator model. So that's this right here. And so we have sold that in quantum mechanics. So when we are going to need to talk about that, we will refer to the results which we had obtained from the previous chapters. Okay, so let's write the total partition function. So the total partition function, as may not be very surprising, is going to have the same components as the energies, right? So Q of M, V, and T is going to be equal to the partition function of the translational times Q rotational times Q vibrational times Q electronic. Alright, and so next what we're going to do is we're going to work on each of these terms. Oh, and we need to put this over in factorial like that. And this is equation 18.19 if you would like to follow along. So we'll just 18.19 to follow along in your book. Alright, so there we have our total function. And so now you see I've color-coded these up here, so we'll just follow along with our color coding. And so we are going to work on the translational one first. So remember that we've already solved for a Q-trans, right? So now we can just talk about how this is going to be similar, right? So Q-trans is going to be a function of V and T again, which is not surprising, is going to be equal to 2 pi M1 plus M2. Alright, so basically we need to have a mass in here, and we've already seen that we had a mass in here before, but now we need to deal with the fact that we have diatomic, right? So we're going to be using both masses, alright? And so, but otherwise, you have V. But otherwise, this equation is rather similar. Alright, so this is our translational part, which I'm coloring red here, to remind ourselves that this is going to correspond with our total energy, because this is the partition function is going to correspond to that energy. And so that is that's what we get for the translational component. Alright, great. So then the next one that we need to look at is we need to look at the electronic. Now we've also already solved for the electronic, so this shouldn't be all that difficult. So let us now work on this term over here. Okay, so our electronic term, we're going to remind ourselves how the potential energy well looks. So let's just draw a little diagram here. So we're going to have the potential energy, and we need to make a couple of terms here. All right, so this is going to be the zero line right here, and so if we make an asymptote, this is going to asymptotically approach the zero, right? And here we're going to take into account the well depth, how far down, so where's the min, that's going to correspond to this value over here. And so this is below zero because it's going to be a negative number, and the negative number then is going to be favorable energy, right, and consistent with our energy values in exothermic and endothermic definitions. Now, we're going to have in here an energy level. Now, this comes from the quantum mechanical calculations, and this is going to be equal to hv over 2. So this is going to be, so this height here, so that's, so if we draw these out like this, right, so we got these various lines. So this line right here, the distance from here to here, which is really the distance from the bottom of the well up to our first level, is going to be equal to hv over 2, where the v is going to be a quantum number. Alright, and so then we're also going to have a distance up here, and these two distances are then going to sum up to the total distance. Alright, so the total height difference then is going to be from this asymptotically approaching 0 down to the well depth. And so this here has the definition of d sub e. Alright, and so d sub e then is equal to the well depth, right, which comes from this well over here. Alright, so that's the difference between the well depth and the first vibrational state. It's going to be so basically this plus this add up to this, right? And so this is then going to be the difference between this and this. And so this is how we get our three different components, right? So these two sum up to give the overall value. Alright, but what we really need is we really actually need the d sub e value. And so that's what is going to go into the electronic partition function. Alright, so when we do our electronic partition function, let's write what it is. So Qelec is going to be equal to, now here's that G showing up again, so that is going to take into account the degeneracy, so E, now this is going to be d sub E. Now you notice I plugged that into the place where we usually put the energy. So we're using the well depth as a measure of the energy here, over kVt, and so then this is also going to be a sum, so we're going to have plus GE2e to the dE over kVt plus blah blah blah, and so then that's going to be an infinite sum. Actually this one is not the well depth, this one is going to be the actual energy, right? So because then as we go up and up, we're going to use higher and higher energy, so this should be negative e to the e2, alright, over kVt, right, yeah, so the well depth is used for the ground state only, which makes sense. because then as we get into the excited states, we're actually talking about things higher and higher up. Alright, so we only need the first two terms for practical purposes once again, so that's really what we actually need, but in fact it is a sum. And so then this here becomes our partition function for the blue contribution. So therefore this Q, this partition function, is the one which corresponds to the energy for the electronic contribution. Alright, so then those are the two terms that are already familiar, and that's how they need to be modified in order to model the diatomic ideal gas. However, we still have two more terms to talk about, so the rotational and the vibrational, and we haven't seen those yet, so let's work on deriving those from scratch. That's what's new. It's worthwhile to note that if we were to extend out to the polyatomic model, so we're doing monatomic and diatomic, if you were going to do something to some nth order, that these are the terms that you would need to have, and so by deriving the monatomic and diatomic, then we've essentially captured the major features that would be needed to describe any gas. Alright, so now we're going to do the vibrational component. Vibrational component. Okay, and so the vibrational component, we're going to start by writing the energy. So I'm going to do E sub V is equal to V plus 1/2, right? Times HV for V equals 1, 0, 1, 3, 3, wow. Okay, this is equation 18.22. Now, a few things to notice. First of all, they seem to be having a shortage of imagination on which variables to use. So we actually have two V's in this equation, and so they don't represent the same thing. Okay, so the V's that have this curly hook on the top, these are the ones that are going to represent the quantum numbers, so these are going to be integer values only, whereas this one is not. This is h nu, and so just to keep that in mind. Alright, so what is this V equal to? So this V is actually related to the force constant of the diatomic molecule, so let's actually write what that is. Equal to K over mu, which is raised to the 1/2 power, over 2 pi. Alright, so you might remember from when we studied basic physics that K is the force constant. So when you have springs, as we have here, so we're assuming that the bond between these is a spring. When you have springs, then springs have a force constant associated with them, and so that's what K is, so that's K. And U is going to be the reduced mass. Alright, and so the reason why we need to have the reduced mass, again, is because we don't have just one mass, we now have two masses. And so, just to remind ourselves, when we have the